Hi, welcome to another edition of Linear Algebra. Today we are going to continue our conversation about matrix algebra, and we're going to take a look at two problems. One related to linear dependence or independence of matrices, and the other one related to commutativity of the matrices. So these are two problems today. You remember in the previous lectures we started talking about matrix algebra. We said the matrices are very much like vectors, so you can add and subtract them just like that. And then we introduced two new operations. One was with respect to transpose, and the other one with respect to multiplication. Multiplication of matrices was quite complicated operation, and it was coming with some surprises for us. That first of all, we have matrix multiplication is still associative. That is an interesting property we did not expect. uh, with respect to transpose, everything was kind of what we expected. One of the new things there was when you do transpose of a product, you get the product of transposes but in reverse order. So that was one of the surprises. And then we emphasized that matrix multiplication in general is not commutative. So perhaps under certain special circumstances it might happen, but it doesn't happen in general. So one of the problems today is going to be in relationship to this, to finding cases that it would be commutative. And so you remember we talked about in the previous lecture we talked about span of a collection of matrices. Under what condition is a matrix in a linear is in the span of the given matrices, or is a linear combination of them. And more interestingly, describing the span itself, finding all matrices that are linear combination of a given set. So for today we have two more problems here to look at. Here are the statement of the problem. Problem 1, a given a set of matrices are given, and we are asked to determine if they are linearly dependent or independent. So here's an example of type 1 question. So we have some matrices given. So for example, 1, 2, 4, 3. So this is say matrix number 1, and then we have matrix number 2, and say this is 2, 1, minus 1, 0. And then we have matrix number 3, and that is nicely just made out of all ones. The question is the collection M1, M2, M3 linearly independent? Are they linearly independent? If they are dependent, find the relationship between them. Okay, so that's number 1. So what was the definition of linear independence? Whatever we were using for vectors, exactly the same thing applies for matrices. Matrices are essentially kind of vectors that are written in kind of a folded fashion as a rectangular array, as opposed to a long vertical or long horizontal array. So how would we investigate linear independence? We make a linear combination of the given matrices with parameters as the coefficients, and we investigate under what condition would the combination be 0. If it turns out, so we look at this equation, one of two things is going to happen. If the only conclusion we get is that C1 and C2 and C3 are all 0, must be 0, in that condition we conclude that they are linearly independent. Otherwise they will be linearly dependent. And whatever information that we get out of that for C1, C2, C3, that is going to be what is going to give us the dependence of them. So that's what I'm going to do. So it says C1 times the first one, 1, 2, 4, 3. C2 times the second one, 2, 1, minus 1, 0. C3 times the last one, 1, 1, 1, 1. And set all of that equal to 0. You remember 0 on the right hand side means just a matrix equal to same dimension as whatever you have on the left hand side. So this is a 0 matrix, not just a 0. Okay, so I go and add them. So 1 times C1, 2 times C2, and 1 times C3, that has to be 0, and so on. So I write 1 C1 plus 2 C2 plus 1 C3 has to be equal to 0. Let me remind you what we targeting here. Maybe I use different colors here. So let's see. I use and here's my 0. I do the same thing for second entry here. So there's going to be 2C1 plus 1C2 plus 1C3 is equal to 0. And then I come here in some order. I do this provided that I apply the same order to all of them. Do it the same way. So minus 1C2 plus 1C3 has to be 0. And finally, C1 times 3, 3C1, and then 0C2, and then 1C3 again has to be equal to 0. So notice what happened. This 1, 2, 4, 3, 1, 2, 4, 3, and then 2, let's see, 2, 1, minus 1, 0, 2, 1, minus 1, 0, and then of course 1, 1, 1, 1. So in an identical fashion, we are converting these three matrices into column vectors. Okay, for example, I put down the first row and then the second row. I do the same thing for all of them. First row and then the second row, and the first row and second row, and the last one of course is just all zeros anyway. So we are converting our inquiry here to a set of equations. Well, now we are back to the very beginning of the semester where we talked about Gaussian elimination and how do we solve these things. So this is a simple enough of a problem that you do by hand, but just so that we have another practice with that software, and then you speed up on doing this type of problems. Let's go to our GAIL software, Gaussian Elimination software. So we say we start with an edit, and then we have 4 equations there. If you want to include the right hand side, which is all zeros, then you need 4 columns as well. But that does not do anything because the right hand side is all 0. So I go ahead and enter my numbers 1, 2, 1, and right hand side is 0, and then it was 2, 1, 1, right hand side is 0, 4, was minus 1 and then 1 and last, right? So it's 0 and then I have 3, 0, 1 and 0. So that was my, this is the matrix, huh? This is what we had here. This is this matrix, and the right hand side 0, I included that. So just double check that the yellow and the blue and the green column matches what we have over here. So that are those are columns, and this is my right hand side. And then I say resume. I go back to elimination mode. So I say here's my pivot, use it to eliminate this, use this pivot again to eliminate this, use this pivot to eliminate that. So what happens in each of those activities that we are doing, it's recorded here as to what happened. Okay, we said the standard thing is to convert to 1 for the pivot, just easier that way. 1. Now I use this as a pivot, eliminate this, use this as a pivot and eliminate that. Now use this as a pivot and eliminate this one. Okay, this is as far as we can go here. We ended up with 1, 1, 1/3, 1/3, and this is the right hand side. This is for C1, C2, C3. Here this C means column, but over there we had the name of our variables were C1, C2, C3, and C4 is for the right hand side. So this is what we ended up with. We go and continue this back on paper. So we go and rewrite this thing. So we did the elimination. We ended up with the following. It was 1, 1, 1/3, 1/3, and everything else was 0. Let's see, double check, make sure we have. Okay, so the last 2 rows got wiped out. Our problem actually does have an answer, so this becomes 0, 0, 0, 0. So remember, this was for C1, C2, C3. Our problem, this is our right hand side. If you write this thing in the traditional notation, it means what? It means 1 C1 plus 1/3 of C3 is equal to 0, and 1 C2 plus 1/3 of C3, that's equal to 0. These rows of zeros are not going to play any role. Now what do we do here? We learned before, our tradition was to call this as t as our parameter. So C2 becomes minus 1/3 of t, and C1 also becomes minus 1/3 of t. So this is our solution. First of all, we were not forced into saying that all c's had to be 0. So we are in this branch. Something else possible, for example, if you want to say get some nice numbers, get this thing so that all of denominators will go away. So I take it to be 3, and C2 becomes minus 1, and C1 also becomes minus 1. Of course, I could take any number here. I could have taken any number. I just take something to clean out the denominators. This means what? This means if I take a minus 1 of this and minus 1 of that and 3 of the last one, I do get 0. So here's an example relationship. Minus 1 of 1, 2, 4, 3. And then, excuse me, let's write minus 1 of second one, 2, 1, minus 1, 0. And then 3 of 1, 1, 1, 1. Indeed gives you 0. Check it. Minus 1, minus 2, plus 3, in fact, is 0. Minus 2, minus 1, and 3 is 0. Minus 4, plus 1, plus 3 is 0. Minus 3 and plus 3 is 0. So we checked, we did 4 check. This is like really 4 zeros here. Everything checks. So what is our conclusion? Our conclusion is that are they linearly independent? The answer was no. The only time you say that is that if you forced into taking all of these things equal to 0. If I had chosen random numbers, chances would have been close to 100% that you get all of these things equal to 0, because your matrices here are not going to support a parameter in general. So here we had some special set of numbers that showed some linear dependence. If they are dependent, find the relationship between them. This is an example. You can write it with a parameter that is, you can multiply this thing by t, and t. That is still 0, no problem. Okay, so that is one style of problem we have. Style number 2, we have brought the issue of matrix multiplication into the mix, and then we said multiple times that we are calling it multiplication, but it's really a complicated operation. We're just borrowing a name from high school and call this thing multiplication. But to remind you again, we had much more going on under this roof. Said, okay, we have something you call multiplication. You have 2 arrays. And then you take the rows of the first and the columns of the second, you dot them the way we learned in chapter 1 how to dot them, and then you write the result in a location which takes its coordinates same as the row of the first matrix and the column of the second matrix you were looking at. You write it in the same spot. So if I had for example row 2 in column 3, so for example if I go to row 2, excuse me, let's see one step, let's go to row 2, and then this one, let's go to column 3. So where do we write the result? Here we write the result in row 2 column 3 of the output. The dot product of these two goes over there. So a very complicated operation. We call it matrix multiplication. Now what do we expect out of this matrix multiplication? Well, we said in general what did we say? We said in general matrix multiplication is not commutative. That's what we said. Is not commutative. Some special cases it was. For example, if the two that you're looking at are the powers of the same matrix, the same rule you had in high school still applies, that you just add up the exponents and it doesn't matter who's first or second. So we had that one. And then now you are going to look at a set of exercises where it asks you to arrange the matrices so that they'll be commutative. For example, in homeworks you come across questions similar to the following. They say let's see. Well, question number 2 was suppose a matrix is given to us. Is a matrix, let's say a general matrix M is given. Let's call it F 2 by 2 A B C D, and some matrix A is given, and that is some special matrix is given, specific matrix is given. And then the question is, well, we know in general, so in general, if you multiply M with A like this or A with M like that, they wouldn't be equal. They wouldn't be, in general, they wouldn't be equal. Now the question is, what should be true about A, B, C, D so that they'll be equal? Find conditions. on A, B, C, D, so that something special happens, which is our matrices are going to be commutative. So again, in general, if you just pull two matrices out of the hat and multiply them, even if you could multiply them, uh, the two answers you get by exchanging who's first, who's second, wouldn't be equal. In general, they wouldn't. Some special cases it would. And here it's saying, well, tell me who is gonna commute with A. So what matrices? So another way of saying the same question is, what matrices commute with A? So that's another style. Well, just write it out. So A, B, C, D, we can multiply it with 1, 1, 0, 1, or you can take 1, 1, 0, 1 as a first entry and then A, B, C, D as a second entry. Of course, you investigate this if they are a square of same size, otherwise that wouldn't be possible. But we want to figure out when does this happen. Well, go ahead and multiply. How did we say we multiply? We had that issue of dot product. We are going to be doing plenty of dot products here. So here, A, B times 1, 0. Well, that's just A. A times 1, B times 0, add them up. Now, do the same thing over and over again. A, B, 1, 1. Who's that? A plus B. A times 1, B times 1, and add them up. C times 1, D times 0. C times 1, D times 1. I want this to be the same as, well, A, B, 1, 1 times AC. That's going to be A plus C. 1, 1 times this. B plus D. 0, 1. So that's going to be just C. 0, 1 times BD. That's just going to be D. So by the looks of it, they contain different things. So in general, they wouldn't be equal. We are investigating when would it be that they are equal to each other. So so how do we proceed? Well, first entry has to match the first entry here. So A has to be A plus C. This has to be A plus B, has to be same as B plus D. And well, C has to be C. Well, it is C. C plus D has to be equal to D. Well, from the first equation, what do we conclude? From first equation, A's cancel. I get here right off the bat that C, this entry has to be 0 for us to get started. Second one, B's cancel. So A has to be equal to D. C equal to C. Well, C is always equal to C. That does not give me anything, so that's always true. These cancel, and again I get C equal to 0. So the upshot of all of this thing is that C has to be 0 and A has to be equal to D. So the matrix that we have here, that matrix M that we started with, this location has to be 0. This location B can be any number, doesn't matter. A and D have to be the same. Like if I put a number A here, here has to be the same number. So D has to be same as A, or A has to be same as D, whichever. This type of a matrix is going to commute with that matrix A that we have chosen. So the two diagonal entries have to be the same. This entry has to be 0, and that entry is arbitrary. So the condition under which that commutativity happens in this particular situation is this. Well, you can go ahead and check it, for example, that, so here we do a check to make sure that our arithmetic is done correctly. So the claim is that if I have A, B, 0, 1, 0A, and multiply it with 1, 1, 0, 1, I get the same thing that if I multiply them in the opposite order, so 0, A, B, 0, and A. So we are at this point, we are checking to see if this is really true. Well, multiply, what do we get? A times 1, B times 0, so this is A, this is A plus B, this is 0, and this is again A. Is that equal on the other side? So I'll get here a 1 times this is 0, times the second one is B plus A, 0 1 times A 0, 0 plus 0, that's just 0, and this times that, I'll get an A. Well, ordinary addition is commutative, so this is same as that, and this equality is true. So if I have this special matrix 1101, it commutes with all matrices whose diagonals are same number, and this off diagonal is 0 and the other off diagonal is totally arbitrary. Okay, so many problems in this section can be approached in this way. So you go back to the original definition to see what the definition says, and if the statement of the problem is slightly different from what we have practiced here, you can still manage to figure out based on the principles we have talked about how to approach them. Okay, so this is going to be a short and sweet lecture, and we are going to be moving on to the inverse of a matrix for the next lecture. And until then, good luck and God bless.